Where's the Hartman? Where's the Hartman?
What?
Yes. Speaker.
Yeah, he was just here.
Dr. Hartman. Dr. Hartman.
Not doctor, only Mr.
Oh,
Hartmann.
Okay, ladies and gentlemen, we'd like to go ahead and get the session underway.
Yes. Yes. Good morning, everyone. Yes, I would like to start this session. My name is Yoshi Kaneda from Japan.
And my name is Randy Bell. I'm the director of the International Data Center, and this is the first session of SnT 2017, Science and Technology 2017. I'm not going to welcome you officially because that will be done tomorrow in the high-level session. So we're just going to get straight into the talks on this session, but I do have a couple small administrative things to say. First, there'll be 2 oral presentations in this session on remote sensing. Then there will be a poster preview session where we go through 1-minute poster summaries of the 9 poster presentations in the remote sensing session. And then there hopefully will be a little bit of time for questions. And I want to emphasize, I've been told to emphasize this app that hopefully you have all received an email and downloaded. Through this app, you can actually pose questions to the panels. And so if you have we can also take questions the old-fashioned way, raising your hand with a microphone walking around. But we're trying out 19th century or 20th century technology, even though we're in the 21st. So if you have it, you can send us questions by this app. So with that, we will introduce our speakers for the oral session.
Yes. Yes, at first, I would like to introduce the first speaker. The first presentation is a remote sensing radar interferometry and precise localization of the North Korean nuclear explosions. Hartman-san, please.
Good morning, ladies and gentlemen, and thank you for the introduction. The utilization of remote sensing made a lot of progress in the recent years, and in the context of the CDBT, radar interferometry, the radar interferometry is a technology which provides information on possible surface depressions after underground nuclear explosions. So I will talk first about radar interferometry with satellite-borne radar data for change detection. The results are a good supplement to the seismic monitoring. So I will talk about some aspects of seismic analysis, in this case correlation of seismic signals and relative localization. And finally, the question, what do we achieve by combination of both technologies? There are a lot of satellites in the orbit for Earth monitoring. I think the Copernicus mission is the most ambitious Earth observation program. Currently, it's operated by the European Commission and the European Space Agency. They operate a number of satellites. There's a Sentinel family, Sentinel-1. These are two polar orbiting satellites for land and ocean monitoring. They performing in the C-band synthetic aperture radar. They are weather independent and they can operate at day and night. They operate at a wavelength of 5.6 centimeters. There are some other parameters given here. Notable is the revisit time of 6 days. This defines also the temporal resolution of interferometry. For the radar interferometry, the satellite is operated in a wide swath mode, so the spatial resolution is 5 to 20 meters. First time radar data are now available in a free and open data access policy. They are online available within 24 hours. And this is important for monitoring purposes. So for in the CTBT contents, this is especially necessary. With this equipment, we can analyze data in the differential SIA interferometry. This data can find change detections in the precision of millimeters or centimeters. So I would like to explain briefly the principle. I use this slide from Professor Bamler from the Technical University Munich. Don't be bothered by the formulas. I won't go into details here, just the principle. We have a satellite which scans a specific area at 2 times. And the measured interferometric phase is related to the difference of the distance between the sensor and the scatterer between both times. So the interferometric phase consists of several parts. There are, for example, the topographic term here and the propagation term, which is related to the conditions in the atmosphere. In our case, most of interest is the terrain motion. This describes the possible terrain motion or subsidence between these 2 times of the images. On the right side, you see the workflow of the processing. So we have the 2 SAR images, which are used for the generation of the interferogram, and then combined with a digital Earth model. So, for example, the topographic phase can be subtracted. The main step of the second part of the processing is the phase unwrapping. This solves the ambiguities which are inherent in the interferometric phase. Finally, we convert the phase data to displacement and get a displacement map. This is the example for such a displacement map. The images were taken on 1st of January and 13th of January 2016. In this time period, the 4th nuclear test took place in North Korea on the 6th of January. This is a section of a 2 by 2 kilometer area out of the whole image of 90 by 108 kilometer. And we see an area of 1.5 to 1 kilometer of service subsidence between 4.5 and 10 centimeters. The coherence is an important parameter to determine the quality of the interferometric phase. So the displacement is determined with high precision if the mean coherence over the whole scheme is high, and then you can if you have a partly decreased coherence in an area of subsidence, this proves the reliability of the estimation of the displacement here. Maybe become clearer if we look at the time intervals before and thereafter. And here you see that the coherence in this specific area is higher than in this time interval, and the displacement, or there's no significant displacement observable. So the close spatial and temporal coincidence of the displacement suggests a correlation with the underground nuclear explosion. Here we transformed the results to a three-dimensional map of the nuclear test site in North Korea. We have here the central facilities of the test site, and 3 kilometers to the northwest, beneath the massif of the Mount Mantap, we have the suppression area. In September 2016, another nuclear explosion took place. At that time, the Sentinel-1 satellite could provide images only 41 days before and 7 days after the explosion, so this time base was too large to get reliable results. But we found another pair of SAR data from the Canadian RADARSAT-2 satellite. The acquisition time was here 24 days, and there are also some other differences to the Sentinel-1 processing, mainly related to the higher resolution of 5 meters, but this means a loss of coherence. And the results are showing here. We have a splitted area of subsidence here. Here's subsidence in the same area as in January, but another area more to the east. Now we want to combine these with seismic observations. The nuclear tests were clearly detected and located by the stations of the International Monitoring System. The error ellipse could be reduced from 880 square kilometers in 2006 to 150 square kilometers in 2016 due to the larger station, the better station coverage. However, within the regional distances, we have only 9 IMS stations, but incorporating additional stations of international earthquake monitoring networks, we can provide a regional localization, and the error ellipse can be reduced further to about 47 kilometers in 2016. Further improvement can be reached if we use relative localization, so the error ellipse can be reduced even to lower values than 1 square kilometer. The prerequisite for the relative localization is the similarity of the seismograms in order to define very precise time differences. Here are an example of one station, Mudanyang. The seismograms are from both nuclear explosions in 2016. In the upper part, the sections show the overlay of the seismic signals for each individual seismic phase. And you can see easily they differ only in the amplitude due to the different magnitude of the events. To quantify this similarity, the coherence is estimated, and the black color marks the high coherence for the individual phases at their dominant frequencies. The most prominent phase is the PN wave, the first arrival. Here this phase is displayed for several stations at different distances and azimuths. And you see the clear similarity. The PN wave vary between the individual stations, but for each station the signals are very similar if you compare the different nuclear explosions. In this case, 3 explosions were selected. These PN waves are now taken and correlated in order to estimate travel time differences. This figure shows the results of the maximum correlation between each 2 events for each station. So each colored square is the maximum correlation value for a couple of events for pair. So, and we have high correlation coefficients between the signals of the events between 2009 and 2016, but a lower correlation in comparison to the event 2006. This is always this first column in this plot here. Further, you can see that the correlation for stations north and west of the nuclear test site is higher than at the east, especially above 1,000 kilometers. So we estimate the travel time differences for each pair of events, and always at the correlation maximum, of course. We could use 103 travel time differences here, where the differences only about some tenths of seconds, so they are small enough to process with a relative location, or to apply a relative location with a double difference algorithm. On the right side, you see the results. So the nuclear explosions between 2009 and 2016 are located within a radius of 450 meters, and only the event 2006 is located about 2,700 meters to the east. The error is lower than, or is around 200 meters. Only for the event 2006 we have a little bit more error here. So finally, we want to combine these results with the results of the radar interferometry to get an absolute location. So you remember this image from this result from the radar interferometry, and we adjust the precise relative location to the results here. We selected the event from 2016 in January as the event for the reference, and fixed this position to the center of the area with the maximum surface displacement. And you see the event in September here is a little bit east to that from January 2016, which correlate also with the results from the radar interferometry. So, okay, finally I have put some conclusions here. Of course, the first two, we identified area subsidence with the INSA analysis, and we could reduce the errors with relative localization. So the results of radar interferometry are consistent with the seismic observations. This is a mean point and contribute to the improvement of the localization. And for the future, satellite-borne radar missions open us avenues to complement the IMS by implementing of remote sensing tools as national technical means. And this needs, of course, further development of the acquisition strategies. Thank you.
Thank you. Thank you very much for the significant presentation. Generally, I can receive some comments and questions after the poster preview session. But the one comment from the Bell-san, please.
Yes, actually, we actually have some questions already submitted by the app. And one of these is, what's the direction of displacement? Is it vertical only that the interferometric SAR is detecting? First of all, let me ask, is that an accurate representation of the question? Yes. Okay.
The displacement is measured in the line of sight, of course. It's not corrected now by the individual directions vertically or horizontally.
Okay.
Okay.
Before we move on, is there briefly any questions that wish to be posed from the floor? Please. I think we have a microphone being... Please use one microphone. I think that they are bringing a microphone.
Just a moment.
But if that takes too long, here, step up and use this one.
Yeah. No.
Sorry, there's a microphone coming right behind you.
Oh, thank you very much. My question is, what's the cost do you think for the subsidence? The cavity collapse or support slap down?
I'm not in the position here to interpret the displacement we have measured with a radar interferometry. This may be, some people think that's a landslide, but it's maybe also such a suppression beneath these mountain mantap, just of collapsing the chamber of the nuclear explosion. And there are interact, of course, the pre-damage of the previous nuclear explosions, maybe, because they are very close together.
Okay, I would like to thank our speaker one more time. And as we move on to our next speaker, I'd like to remind those who have 1-minute poster previews to assemble over here in this area, because as soon as the next talk is completed, we will move right into the poster previews.
Okay. Thank you, Hartmann-san. Then next, I would like to introduce the next presentation. The satellite-borne video, the processing and the reporting the techniques for the imaginary analysis. Ratquist-san, please.
Thank you. Thank you to the chairs and the other participants in this session, and thank you for showing up this early Monday morning. Today I'm going to discuss with you some of the benefits and some of the challenges posed by spaceborne video processing. Just one second. What I'll show you this morning is a peek into what we can expect in the next few years. What's peculiar about the presentation that I'll give is if I was giving this in 2013 or 2015 at this conference, I would have been a lot more optimistic. I would have told you that in 2017, we'd be watching daily video feeds from outer space, but that's not the case right now. I'm going to go through some of the reasons why that is. Let's see. Some of the sensors that do exist right now, some of the data that we can extract from those sensors, and I'll give you some examples of the video of what it looks like. So to begin, we'll look at one of the 2 companies that are distributing video from outer space right now. It's EarthCast. It's from Canada, and they have many international partners. Here's a picture of the sensor aboard the International Space Station. We can see a 3-day orbital path of the ISS, which, if I can get this, well, that's not working. In the lower left-hand corner, we can see a 3-day orbital path of the ISS. Sorry. Yeah. So here we can see the orbital path, and we can see a fairly high revisit rate just by attaching the sensor to the ISS. And here in the lower right-hand corner, we can see some of the data. This is a multispectral video using a Bayer filter. Moving on to what is perhaps a slightly more interesting sensor is the constellation called SkySat. Right now, they have 7 satellites in orbit. And this is going back to this 2013 or 2015 idea that I mentioned about much more data being available. Back in 2009, they started as Skybox Imaging. In 2014, they were bought by Google, and they changed their name to Terabella. So at that point, they were releasing some test data, and this is the data that I'll show in a few minutes. When Google purchased it, they weren't sure how they were going to expose the data to users or to consumers. And so as scientists, we were waiting to see what Google would do. And then earlier this year, Google sold the company to another remote sensing organization called Planet. And Planet isn't sure what they're going to do or how they're going to make that data available. So right now, we have limited access to this sensor. But what's interesting to point out about this sensor is its idea. And we'll see that potentially the new video sensors coming out will look something like these. These are small CubeSat sensors, and we can see it in the lower right-hand corner. This is the SkySat 1 before it was launched. It's about the size of a washing machine. Some of the specifications that we can expect from based on this sensor and the success that it's had so far, is about a 90-second hover time over an area of interest. And we'll look at this videos of this in just a second. And we have a 1-meter spatial resolution on this. Now, they offer 3 different products, and we'll get to see some of those. The stabilized video, which I think you'll all end up purchasing if you do it, because we'll show you the unstabilized first, and if you have vertigo, you might need to leave the room. But additionally, we can get the raw frames, and this is the stuff that's maybe potentially a little more valuable, and I'll show you some of the products that we can derive from that in a minute. But alas, the data still isn't available from Planet. They claim that they're still looking into how to distribute this data to consumers. This is a screenshot from Planet's website of the data that is available. But new companies are also looking into this. EarthEye is one of those who plans to launch a constellation of their own. And here we can see that their sensor looks very similar to the SkySat sensors. But what I find most interesting about this and some of the other ventures into video is that their quote from their website that they're looking for the ability to accurately film moving targets in colored video, such as vehicles, vessels, and aircrafts. And this could be very pertinent to monitoring some specific activities on a site for the CTBT. So here's an example, and this is the unstabilized video over Las Vegas. And here we can see lots of moving cars. We can observe a lot of activity on the ground. And this is expected to see in an urban environment. And of course, this is interesting for a lot of different scientists for monitoring urban activity. But of course, here in this conference, we're mostly interested in some other parts of the world. So we'll go on to the next video. This is over Yangbyang and DPRK, and this is the data that I'll show you later is derived from this scene alone. Here we can see that there's little activity on a site, but this is what we expect in normal nuclear complexes, that there's not much activity. You can see some clouds moving by, and there are some indications that things are happening there, but for this presentation, we won't go into that. Now, I'm not here to sell you on video, but EarthCast is, so I thought it's fair to give them a chance on showing how they can use video for imagery analysis. I think this one. No, sorry. Can you execute the play from there? No.
Which one to execute it? Just press.
Yeah, there it is. There it is. We can, it seems to be working now. So, sorry. And we can already see one of the problems with video is technology. So this is a ballistic missile site in Iran, and this demonstrates some of the possibilities. They were able to detect staff personnel moving throughout the site. In addition, they could glean some of the same information that's available from other satellite images, different signatures of a ballistic missile site. And of course, this can lend itself to a lot of observations that are pertinent to the CTBT. As I mentioned, the multispectral is also interesting compared to the SkySat. But unfortunately, like most technology, software gets in the way. And because a lot of this data isn't readily available, a lot of the traditional remote sensing software packages don't handle this in a very advanced way. And what I mean by that is there are some workflows that have been developed for UAVs which can be adapted to this, but because the UAVs use trajectory information that's not available for these types of sensors from outer space, the workflows do differ significantly. The video editing in these remote sensing software packages are limited. And the geospatial interaction is also limited, so that if you have GIS or CAD layers that you want to include in your analysis, you will have to work pretty diligently to get that to work. But there is adapted software. There are, of course, lots of libraries for video editing, but that needs to be recognized as a potential problem for an organization that wants to obtain this type of information, but not also hire on several video editors to handle the data. And there are models for data extraction that can be developed or are developed for such things. Now, the study site, some of the information that I'm going to show you that we derived was a comparison on what video data can look like for developing surface models versus traditional stereo acquisition of other very high resolution satellite images. And we went through a lot of data, and we won't have time to look through all of these, but this is a diagram showing the acquisition, the stereo convergence angles of the acquisition of any two scenes that were compared. So to move on, we'll look first at the SRTM 90-meter resolution data over Yongbyon. And here we can see that there's not much valuable information for at least visual interpretation, although this is a very powerful data set on its own. But if we move ahead to 2013, using the Pleiad stereo acquisition, we can start to see a lot of buildings around the 5 megawatt reactor in the Yongbyon complex. We get a lot of dropouts because of the water, and the data is a little noisy because the stereo convergence angle is very small. Here, where we have a larger stereo convergence angle with a GOI-1 data set, we see some more valuable information, but because of the data where it was acquired, we see a lot of occlusion happening here so that we have a lot of data dropouts as well. If we take just 2 of the video frames that were collected from the SkySat sensor, we can see that we also have a lot of dropout. Again, if we pick a different pair, we see lots of dropout. But if we take 120 of those and average them together, we can start to see some very valuable surface models being generated. In addition, we can take some cross-sections from these surface models and then develop these surface models into more complex models that might help with the analysis. So to summarize what we see that spaceborne satellite video sensors will become more common, but when they're made available to us is still unknown. We'll see new constellations. We'll see the processing software that it will adapt, but again, they're struggling with the same thing that we have, is that it's minimum test data. We need a lot more use cases for this type of information. Video does offer some unique possibilities, especially in an event of a test case or an alleged test case. We can see that if we capture the data, that could offer some valuable insight into what occurred as compared to other Earth observation information. But it does have a short duration period and a small geographic footprint, which may cause problems. The data processing offers additional data sets, such as the surface model that we demonstrated. And some possible applications to the CTBT are, of course, to support the on-site inspections. You can imagine if this data was able to be processed quickly, this could give a lending hand to the scientists on site, and also complement some of the IMS activities as demonstrated in the previous presentation. And with that, I thank you for your attention.
Thank you very much, Ratkos.
Okay, we have time for perhaps a question. I have one question on the app, but I think this is a more generic question. Are there any questions from the floor? I see one back here. Can we get the microphone over to this gentleman? Oh, they're coming around the column.
Yes, very interesting talk. Have you done any analysis of sites that you can access physically so that you can do ground truthing to compare your reconstruction accuracy with the actual measurements that you can make on the ground?
We haven't, and the reason is twofold. One is that up until recently, EarthCast was not making the necessary information for processing available. So when you buy this information, if it's just as a straight video feed, it's not valuable for remote sensing computations. Recently, they came up with they now have the capability to conduct this. So I think we will in the future with EarthCast data. With the Skybox data, not much data is available for these sites. So we haven't yet, but that's definitely on our list of things to do.
Okay, and quickly, what software are you using for your analysis? Is it open source or proprietary?
It's mostly code developed by DLR, but we've evaluated maybe the top 5 commercial off-the-shelf remote sensing software processing for these.
Thank you.
Thanks.
Okay. Thank you very much. Yes, thank you very much, Ratko-san. So I would like to move on the poster preview session. Please come to from the D.3 poster 1, please.
So the way these poster previews will work is and this would be a lesson for all of you who will have poster previews later. You'll assemble, and then you'll all stand next to each other, and you'll be coming up to the podium one at a time, and you'll have 1 minute, that is 60 seconds, to present your one slide that advertises your poster. This is fairly rapid, and there's no time between, time between these presentations. So if, I don't know, which one is first? You want to, whoever's number 1, would you please take the podium? I have to admit, I don't know which poster will be first. So why don't we go ahead and put the first poster up, and someone run up to the podium and...
Yes.
Can we go ahead and put the first poster up? Because they won't know which one it is until that first one is shown on the screen. All right, your clock is ticking. Whoever this is better run up and present. That's why we ask people to assemble at the front.
Please.
Hello everyone, my name is Ivan Iliev. I'm a PhD student in Sofia University in Bulgaria, and I also work for a private company, Tito Consult. We work together on this project. This is an implementation of airborne gamma spectrometry survey of a certain area. We can recognize different isotopes with one flight, and we can also build an image preview of the ground, even a 3D image. And please have a look at the poster outside. It's number P2 on the session 3.3. Thank you.
Thank you very much. Next, please.
So working with a stack of RadarSat-2 imagery and multispectral images, this poster describes our attempts to locate OSI-relevant observables, surface observables, which were generated as part of the integrated field exercise in 2014. It's poster number 3.3-4. So come and have a chat later on.
Thank you. Thank you. Next, please. Please.
Okay, so the title is Subsurface, Surface, and Remote Observations of Legacy Nuclear Explosion Sites, but a better title would be From Ground Truth to Space, because we have a whole suite of data sets. It's a very data-rich poster, and I encourage you all to come. We also have some algorithm development, and this integrated work helps to build confidence in remote sensing methods. Thank you.
Thank you. Next, please.
Good morning. My name is Ralph Kaiser. I'm the head of the physics section at the IAEA. After the Fukushima accident in 2011, we figured, wouldn't it be nice to have a small unmanned aerial vehicle that could do some remote sensing now, that we could send in, do some autonomous mapping and provide us with radiation data without having to send in people to take those data. And, well, such a system was not available, but basically the technology was. We started to develop our own system based on what was available then and the requirements locally told to us from Fukushima Prefecture. We've delivered such a prototype system to Fukushima Prefecture last summer, and we now have about 4 years of practical experience in using unmanned aerial vehicles. Please come and see me this afternoon. I'll be happy to talk to you about all the technical details. Thank you.
Thank you very much.
I think that's all the poster previews we had.
Yes. There's a poster session today afternoon from the 4 p.m. in the Westsaal. Please come to poster session at T3.3, okay?
And with that, we're going to conclude this session because the next session, the app has already told me, will be on the podium in approximately 90 seconds. So we must do a quick change, and the next session will begin promptly. Thank you. One administrative point I will make, those of you who have these 1 minute, 1 slide poster previews, if you've uploaded them, please verify with the technicians at the side of at the respective session that your 1 minute summary slide has been received and is loaded in the deck for that particular session. Thank you.
Okay. Good morning and welcome to the next session, which is called Fusion of Data from Different Monitoring Technologies. My name is Anders Ringbom. I will be the chair of this one. Let me first say that we only have we have 2 talks scheduled for this session, but we only have one that actually will occur. That's the first one by Ole Ross here. So I guess we will have then, if there's not a lot of questions, we have a short break and then we have the poster session after. So at the scheduled time, 10:15. So, okay, so let's then start with our talk, which is Atmospheric Transport Modeling and Radionuclide Analysis for the MP215 scenario by Ole Ross. Please.
Thank you, Anders, for the introduction, and good morning, everyone. The German NDC tasks are tackled by different institutions. So the NDC is located in Hanover at the BGR, where the waveform techniques are based, and for the radionuclide analysis and the station operation of the Schauensland station, RN33, we are supported by the Federal Office for Radiation Protection. So this is a common endeavor, and for those of you who are new into the NPE business, the National Data Center Preparedness Exercises are simulated scenarios of treaty violations, though normally there is a real waveform event, in the best case an explosion, and a simulated radionuclide part, which then has to be analyzed by the participating NDCs. And there is a now history of 7 NPE scenarios, which were organized by the German NDC since 2007. But there was now the new thing in 2015 that the German NDC wanted to participate. And so the radionuclide part of the scenario was created by an international control team from various countries, coordinated by the Austrian NDC. And for the first time, artificial radionuclide spectra were in the exercise. So the scenario in 2015 looked like that there were some rumors about suspicious behavior in a fictitious state, which is located here. It's called NPDOR. And this region should be monitored closely for 2 months in the November-December 2015. And the region was chosen because there is regular seismicity in this region. So there's a Lubin mining area where mining-induced earthquakes take place quite regularly. So this is for the beginning of 2015, from January to August, in a magnitude range which is suitable for NPE scenarios, so around 0, but sometimes even higher. And then the idea was that the radionuclide control team should choose an event without our knowledge in this period and then set on top the radionuclide scenario as soon as they have chosen an event. And then generate spectra. So this exercise started in November, and the seismologist could already start in looking for events in NPDOR, but it then took some time, actually I think until March 2016, that the radionuclide scenario was ready, because they had some need for coordination of creating of all the spectra and things. And then this work started for the colleagues at BFS in analyzing this huge amount of artificial spectra. The way they did it was first with automatic analysis, so with Atami and Unisampo Shaman, and only for a few spectra then they did a manual reanalysis, so for the most interesting or most crowded ones. There were also some issues in spectra analysis occurring, so some difficulties so it was of different kind, was not as easy. But the overall picture was that you had a lot of stations down here with many isotopes in the spectra and quite high activity concentrations. SnT was also quite high. It's on the wrong side of the line in this part. And you had here spectra with also remarkable concentrations, but but less isotopes in it. So this was a qualitative picture that there was a twofold domain. Now going into the quantitative analysis, if you tried to get a time zero, so explosion timing over isotopic ratios, the zirconium neodymium 95 clock had quite a variation, but you could get a time of explosion on rather 16th of October 2015, which was not consistent to the analysis of the xenon isotopes, or the xenon isotopes weren't consistent in itself, so it was not possible to have a event timing over the corresponding xenon isotope ratios. There was no common clock in it, and if you then look into the 4-isotope plot for the discrimination thing, the values which were analyzed in Freiburg were a bit more to the explosion domain, so there was another mixture than a normal background, which is indicated by this ellipse. But I think it is due to difficulties in the xenon 131M, which wasn't actually really present in the samples. There's a large uncertainty, and it doesn't follow a common clock, because you see this is a later sample with a fresher mixture according to decay, so it was not consistent. There had to be some mixing. Coming then to atmospheric transport modeling, for those samples we performed high resolution backward modeling with high split and now overlap the source regions. But there were quite long transport times, and some of the stations are down here outside the map. But you have a high coincidence on the 15th of October over NPDOR. So you would state that it's plausible or consistent that the release came from there. And then there are also 2 REB events on the 15th. So we took one of them and made a comparative forward simulations, also with high split. Now with 0.5 degree GDAS data. The latter one was with 0.2 degree ECMWF data. And the detection pattern which comes out, so which stations are affected, fits well to the scenario. So in principle, you would say, yes, this is a promising event candidate, but you have still these inconsistencies with the isotopic content of the sample, because now the more probable source time was on the 15th, but the timing gave the 16th. Xenon timing wasn't consistent at all, so there had to be additional sources. But how to look for them? We looked for REB events with associated infrasound detections, because of course events close to the surface could be associated with infrasound emission. Of those we took also one for a forward simulation, but this didn't fit at all. It was not possible to match the scenario with those other events we took into account. Looking again backward from the Schaumsland station, the RN33, for the possible source region of the second event, you get a source region here in the Western Europe, but no indication where exactly to go. So this is the point where we didn't know how to proceed. but the recommendation at this stage would have been to say, okay, we have one location where emission could have taken place and a seismic event was, so go there for an OSI. This is where we have to go. Of course, there is ambiguity, and you can discuss if the ambiguity is the reason for OSI or will impede the possibility to request an OSI. And of course, on the seismological side, it was clear that this was a mining-induced earthquake. Nikolai Gestermann has a poster on this analysis. So the actual solution of the whole thing was that the scenario team invented 2 nuclear explosions. And for the first time in the NPE series, it was that way. And actually, the other small atmospheric nuclear explosion was here in this region, where then the plume from the first explosion passed over, so that it was even harder to distinguish between the sources from the southern stations. But there was no clue, no idea how to find or to localize this second event. The NPE series should continue, but we need, of course, some institution who provides a scenario. There is a discussion of the possible next NPE in the NDC meeting on Wednesday afternoon, and volunteers are welcome to contribute to this. Thank you.
Thank you very much, Ole. So, do we have any questions from the audience? I see no questions in the app so far. No questions? Okay, so in that case, we thank you again. And actually, I was misinformed. We have a second speaker. She's here. So we will have a second talk now. Which is investigation options to visualize the technical data generated during an OSI. By Jennifer Stefanovic, please.
Good morning, everybody. So I believe this is actually my poster preview that's up right now, rather than my talk. Sorry, everybody, for the confusion. So this is the poster preview rather than my presentation.
Talk up, please.
Okay, here we go. Okay, so my talk today focuses a little bit on on-site inspection and some of the technical data generated during an on-site inspection. My colleague James Palmer and I have been investigating some software in order to represent this data really in a way that's integrated across all the different techniques and can actually add some benefit to an inspection team. So I'm going to talk a little bit about the context of the work and our motivation for it, you know, like outline the problem, talk about our approach, and then I'm going to show some examples of some of the technical data that was generated during the integrated field exercise in Jordan. I'll touch on 2D cross-sectional data, 3D volumetric data, survey line data, so some of the near-surface geophysics techniques that are used during the IFE, and then talk about complex data types, the seismic and the radionuclide data. And then I'll just go through some conclusions. So the problem statement really is that we have all these very disparate data types that we want to try and integrate during an on-site inspection to kind of add value for the inspection team, because you may have experts in various techniques, seismic techniques, multispectral imaging, but what you really want is for the entire inspection team to have a good understanding of what the data is showing for all these different techniques. And here you can just see some of the many different data types that are generated during an on-site inspection. You have multispectral imagery, conventional imagery, you have some gravity anomalies there as well. And we want to be able to put all of these different data types into one place so we can really get a feel for what the data is telling us and start to pick out some anomalies. So this is just to show that during the on-site inspection we have many different techniques. So we have seismic, resistivity, GPR, magnetic data. Those are just some examples. And from each of these data types, we can generate several different data products. So for seismic, you have event location, station location, the traces themselves. You have cross-sections that you generate from resistivity and from some of the other techniques. And then here we have just several different ways that we might want to display data in an integrated fashion. You might want to generate voxels, point cloud shapefiles. You can generate CAD models. And what I'm just showing here basically is that in all of these cases, there's a many-to-many mapping. So there's some complexity here in how you want to, and there's some choices to be made in how you want to represent this data. So most of the data that we use in this study came from the integrated field exercise. Most of you will be aware of that and very familiar with it by this point. But the inspection team really needs to collate and integrate all of this data so that the entire inspection team can get a good understanding of what's being shown. And at the initiation of an on-site inspection, you have some data types, you have cartographic, you have maps, you have topography, you have geology of the area potentially. And then once the inspection gets underway, you want to potentially be able to track your field teams in real time for health and safety, like from a health and safety perspective. And then you generate some of these technical data types and you want to be able to integrate all of them. So we had a look at several different software packages to see how we could try to integrate all of this in a 3D environment so that it makes it a little bit easier to visualize the data. And we came across this software package called GeoVisionary, which is, it was designed by the British Geological Survey in association with Vitalis, which is a software company. And it was essentially designed for this purpose, for the BGS. But you can integrate all these different data types. It's very powerful in that it can take lots of native data formats and kind of you can visualize them in the GeoVisionary program itself. So we picked 4 different types of treaty-relevant data to display, and then we assessed them in relation to the ease with which they can be visualized, and then the value added to the inspection team by visualizing the data in this way. So the first example here is just standard imagery. This kind of data will be collected during an initial overflight in an inspection area. And you can see you can combine these data types to produce these ortho images using photogrammetry. The benefits to doing this are you get some very high resolution topography to supplement your kind of the shuttle data sets that you get prior to an on-site inspection. And it will improve your understanding of sites for mission planning and give you a better idea of what your sites of interest actually look like. Some of the downsides of this is that you need the software to construct the image before it can be loaded into GeoVisionary. It can take some significant time, and you also need many images of the same area to create a good quality photogrammetry ortho image. But you can then use this. So this is just a rendering of that in GeoVisionary. You can really see the higher resolution data set that you get from this. And then again, you can use that to plan your missions and So you can use it also for what we call digital fieldwork. So if you want to tell a field team, tomorrow we want samples from these locations, it's very easy for them to get a feel for that. And again, you can see that there against the backdrop of the satellite data. So there is a real improvement to be made there. Okay, so we also use this with cross-sectional data. Again, the power here is that you can see the subsurface and surface data in parallel, and you can get a good idea of the context of that data. You can also use GeoVisionary to manipulate the data sets. If you only wanted to see the anomalies, you can kind of blank some data out. And again, you can combine data sets here. So later on I show we have some magnetic data over the resistivity survey, and you can see an anomaly that maps to both data sets, and it's really quite powerful. Again, there are some choices to be made here in terms of sampling, resampling, and interpolation, and all of that processing has to be done prior to GeoVisionary. But once you have that kind of pipeline set up, it's very easy to load these kinds of data into GeoVisionary. Okay, so in terms of complex data, we have seismic data, and I call it complex data because from the sense of the entire inspectorate, they're not necessarily going to care about the traces themselves, the seismograms themselves. What they want to know is, where is the event location, how well is that location characterized, what is the accuracy of that data set, how many different SAM stations actually observed that event. And you can take complex data and you can have a simple output. So how do you want to represent this? You have X, Y, Z from your location of the event or the station. You can, from the magnitude of the event, you can have a colour scale, for example, the number of stations to observe an event, where you can just represent that very simply with the number of points on the star, for example. And then here is just one example of that. And if I skip forward a couple, you can see a kind of broader context. This is polygon 29 down here. And again, these are the real locations of events that were observed during the IFE, with some of the stations that recognise those events and the accuracy. Okay, so just to wrap up, the ability to visualise all these different data types kind of in an integrated fashion is going to be very powerful during an on-site inspection. You can use GeoVisionary or tools similar to this for mission planning, logistics. You can use it to interpret your treaty-relevant data. And you can also use it as a briefing tool for various stakeholders, the inspector state party. It might make it easier to kind of view all of this data, and then subsequently after an on-site inspection when you come back here to Vienna. However, there is some careful thought that's needed for how to display this information. There's a little bit of thinking that needs to happen before you can put all of this into GeoVisionary. But that kind of pipeline will be set up by the experts, and then GeoVisionary is just a tool that you use for the entire inspection team, so they can all have a shared understanding of what the data is showing. I guess the output of this really is that tools of this nature should add value for the entire inspection team and not unwanted complexity. So I guess that's it really. Any questions?
Thank you very much. So, any questions or comments?
Okay.
Yes, please. We have a microphone there.
If I were thinking about seismic data for an on-site inspection, I would think in terms of nodal arrays of 10,000 or more instruments being deployed at the same time. Have you given consideration to that sort of thing in your displays?
So you're talking about the IMS data that would go into the prior to an on-site inspection? Okay, so in that case, in terms of the seismic aftershock monitoring, the SAMS system, it's very unlikely that the inspection team will actually deploy that many instruments. I mean, during the IFE, they didn't deploy, as many instruments as they were expecting, and you have to be realistic with the data sets that you expect to have. I think as time goes on, and we get better at potentially deploying these seismic arrays, or we get kind of more efficient overall with the process. The kind of thing that you're talking about is what the seismic analysts will do prior to the display of this information. So geovisionary is not an analysis tool, it's a visualization tool. So the number of, the amount of data that you want to integrate into this will kind of happen behind the scenes, and then you will just see the output in geovisionary. Okay.
We have time for a couple of more questions. Yes, over there. Please.
Thank you for your presentation. My question was just on the overflight imagery.
Okay.
You mentioned that could be processed and passed to the inspectors so they had a better idea going into the site. How long would that take to process using your software?
So it really depends on the number of images you want to use to create your ortho image, but we can run a program like that on maybe like 10-15 minutes, something like that. Is that how long it takes, James, to generate? So what James was just saying is that the processing of those ortho images happens behind the scenes again before it gets loaded into geovisionary. But I think the question was more around how long that would take to generate.
So for those data sets, they were done on, well, the one data set that was shown was from the one of the sort of half the area that was flown during the additional overflight, capturing the aerial imagery using the MSIR equipment set. That processing was done on a workstation laptop, and this was the first time that we looked at doing this sort of processing, but once with an established workflow or pipeline, however you want to describe the process, that you go from receiving imagery off the overflight to producing a data product that can go into something like geovisionary, I would expect 48 hours tops, depending on the number of images, how efficiently you've set up your process. I would, if you had time to produce a very well nailed down process, I would be confident to say 48 hours. I would expect significantly less time than that.
Thank you.
Thank you. So, do you have any more questions? If not, we thank both the speakers again. Thank you.
Thank you.
So now it's time for the poster preview. So I don't know how many we have, just one or two. So do we have the poster presenters? It's you? Okay. Start rolling this. All right. Please.
Good morning, everyone. My name is Hakim Gaddou, radionuclide officer at the CTBTO. The poster is about the CTBTO contribution to NDC Preparedness Exercise 2015 in terms of spectral data generation. And we mainly describe the methodology which consisted of Monte Carlo simulation of the artificial part. Then the simulation was combined with the actual background sample spectra using a new ad hoc software tool. Then the contribution was also extended to data testing in terms of consistency with the specifications for formats IMS 2.0. Thank you.
Thank you. I think that's it. Yeah, okay, so that's the only poster preview we had. So then I guess we can close this session, and thanks all the speakers again. Thank you. Okay, good. We're closed.
Yeah? Yes. Yes, in 15 minutes. 10:30. 10:30. This one finishes a bit early. Yeah, who should announce it? Me?
isn't a way to increase the audience light without increasing the whole light, is there? It's just one. Are there different bands? Because I hardly, when I have to film the audience, it's so dark.
It's too dark. Yeah. So for my taste, it's too dark.
Yeah.
But
someone asked you to turn the lights down.
I didn't want to do it because I know I'm here 5 days, and after 5 days in darkness.
It's bad, yeah. Do you know who it was? I have to find out if it's my boss because.
It was a younger guy, very jacket.
Well, let's try increasing them a little bit and see if anybody complains. If they complain, send them to me over there.
Okay.
And if it's my boss, then I say, oh, I'm so sorry.
Okay.
And if it's not, I tell him to.
Okay.
Good morning, ladies and gentlemen. I'd request everybody to be seated, please, so that we can get the session started. If there are any speakers for this session who are doing poster presentations, I request that they please come and sit up here in the front. We'll begin the session with the oral, which will be about 15 minutes, followed by some questions. And soon after that, we'll start with the poster sessions, which will be 1 minute each till we go through all the posters. So just to remind everybody, this session is historical data from nuclear tests and testing. Our first speaker today is going to be Brian Milbratt. A short introduction. Brian is a technical staff researcher at PNNL Labs in the USA, and his work has been with the CTBTO, assisting technically with the on-site inspections, especially with radionuclide measurements. And he also works in the US on developing radiation sensors and detectors for non-proliferation and other purposes. So without much ado, I give it to Brian.
Thank you. As Nick mentioned, I'm at PNNL along with my co-author Jonathan Burnett, who just got married this weekend. And our talk is extrapolating radionuclide observables for OSI-like scenarios from an American underground nuclear explosive test that was called PLAT. So PLAT was an American underground nuclear explosive test that occurred in April of 1962, soon after the end of the 3-year moratorium on testing that the U.S. observed from 1958 to 1961. And it represents the early days of the U.S. efforts to conduct and contain underground nuclear explosions. They had done a few before the moratorium, but they started in earnest after the moratorium. And it was also one of the early U.S. tests to do a horizontal or tunnel emplacement into the side of a mesa at the Nevada test site, which is now known as the Nevada National Security Site, or NNSS. The depth of burial for PLAT was 171 meters, and it was a 1.85 kiloton test yield. I don't have a picture of PLAT, but I do have a picture of Des Moines, which happened in the same mesa with similar results, unfortunately, for the U.S. A couple months later. Here you can see Des Moines. PLAT and Des Moines are prominent rivers in the U.S. Midwest. You can see Des Moines leaking as well, and this is rockfall that you see down the side of this mesa from the seismic event. This is a shot I took of PLAT a few years ago, the site. Probably from about 400 meters away, you see a series of, some of these are tunnels, some of these are little more than storage bins in the side of the hill. That's about 170 meters level to the top. That is a pretty steep slope up to here. You can do it if you're physically fit, and then it gets even steeper from about here on. Des Moines was over on this end, and PLAT is actually just right off the end of the picture. So PLAT was a prompt release. It vented almost immediately, 1.5 seconds from the portal, from fissures that opened up on the side of the mesa up to the top, and from a tunnel ventilation hole. It also leaked. And so they got a pretty complete set of particulates. The ones that the U.S. identified in its monitoring at the time were zirconium and niobium 95. ruthenium 103 and 105, iodines 131, 133, and 135, tellurium 132, barium lanthanum 140, and cerium 141 and 144. It had a cloud height, the release did, of 2.5 kilometers. That cloud drifted north at 29 kilometers an hour, and it was detected within the U.S. monitoring system at the time up to 200 kilometers away, and had a fairly large release activity of, as determined at 12 hours after release, of 7 times 10 to the 17 becquerels. So we, John and I, wanted to model this release for the purpose of trying to generate plumes like one might be looking for in an OSI. Now, if you're going to model a release, some things are pretty standard to do. You can get your isotope inventory using fission product yield data from a publication like England and Ryder. The fact that this was a prompt release we were modeling meant that we didn't really have to worry about various decay chain considerations happening before the release time. There's actual measurements from Platt, which I'll show at the next slide, that help us to constrain what the percentage release was of the event. Fractionation, if you're trying to model a nuclear event, is really the big gorilla. Fractionation can vary quite a bit from one release to another. However, in this case, this being a prompt release where there were a lot of radioisotopes species detected, would put the fractionation that did occur kind of at the minimum end of possible fractionations. And then the dispersion and the deposition that we did for our model. We used high split, and we used actual meteorological data from the time. So Platt occurred kind of at the northern end of the Nevada test site, and then the U.S. had monitoring stations around, and one that detected a lot of radiation was at Queen City Summit. Summit just means kind of a high point in the road, this state highway. They had air monitors there that measured various iodine isotopes and also tellurium in concentrations between the several isotopes of 100 to 1,000 becquerels per cubic meter as the plume passed. And Queen City Summit is 63 kilometers from the explosion. It's probably about 120 kilometers from the explosion site to the city of Las Vegas. Now, using high split, we determined a dilution factor from the site to Queen City Summit of about 1 times 10 to the minus 12. And that gave us a release fraction of the event of about 1/3%, 0.36%. So using that information, then, we can make plume models, plume maps for Platt, like one would use in an OSI. And here we've done that. We have various fractions of the release per meter squared plotted out, e to the minus 9 to e to the minus 12. You see it diluting as you get further from the explosion site. This table here, and then you can, using that, high split will also let you deposit that onto the ground as the plume passes. And these were the activities from high split that one got on the ground surface at Queen City Summit right when the plume passed. So that was like 2 or 3 hours after the nuclear explosion. Unfortunately, in 1962, the U.S. did not take soil samples at Queen City Summit, so we can't directly compare them, but there were water samples and vegetation samples that correlate to those. Here we've drawn a couple imaginary inspection areas, both maybe having plumes over about on the order of 10% of the 1,000 square kilometer inspection area. And using MDAs, that minimum detectable activities from the IFE14 effort for soil samples at the IFE14 lab, where they did overnight measurements of soil samples, we analyzed those measurements to see what sort of minimum detectable activities the lab was capable of at IFE14. And we calculated how long the OSI relevant radionuclides would have been detectable in this Platt plume event for if soil samples were taken like done at IFE14. A being again the near one, and then B being the one farther away where the activities were about 2 orders of magnitude less. For the near site, you see a lot of, this is how long they would have been measurable at the MDAs. Some isotopes were even measurable over 2 years away for the site that contained the vent location. For B, for the farther away site, all of them had decayed at some point prior to, below the MDA level, at some point prior to 2 years. A dashed line means that they were never measurable, at least from a 1 week to 2 year time span. So you see, for example, for the far away OSI site, some of your longer lived isotopes never have enough activity to be measurable. So in conclusion, we've used measurement data from a US low-yield UNE release, coupled it with the actual MET data and some measurements that were made at the time, and generated a deposition plume model for the UNE. And our hope is that models like this and others can inform the kinds of particulate radioisotope activities that might be present in an OSI, how long they might be detectable via soil samples or survey techniques, and so forth. Now, although that percent release, 1/3%, is larger than most US releases were from underground nuclear explosions, I will point out that it is not large for the US prompt releases that involved many isotopes. It's actually fairly representative of those kinds of releases. 2 important areas that we did not study, but that I'll mention are needed for further study, are noble gas releases, which then deposit out into particulates, and what the depositions look like very near the release location. For the very close-in deposits, that gets a little more complicated than one can do with high split, and further effort is needed there. I visited Platt myself a few years ago, and I thought I'd show you a couple pictures. This is the entrance to Platt. A rock slide, either at the time or later, has blocked it in part, but I was still able to, and this is still a rad area, I was able to climb down into the tunnel, and there I am at the entrance tunnel to Platt. There is a door further back, so I couldn't have gone too far, don't worry. If you're curious, using this link to an article John and I wrote, you can see a video of the Platt release. This is a still from that video. Here you see the initial vent and some rock fall occurring in the area during the event. Thank you.
Oh, thank you very much. Questions? Okay, no questions. Well, no questions. Thank you for interesting presentation. Okay, now we continue with the poster preview session, and I believe that all speakers remember that they have 1 minute for presentation. Please, the first speaker has the floor. Who from the presentations will begin? Where is the list?
Yeah.
Oh, okay.
So we can move on to the second poster presenter, please. Autumn Bordner. No?
Also, no.
Okay. The third, Anna Dobrinina.
Okay. Fortunately, we have.
Good morning. My name is Anna Dobrinina, and my poster shows the first results of the treatment of the seismograms of 9 peaceful nuclear explosions conducted in the former USSR in the territory of Eastern Siberia and Yakutia in the last century. These events were measured by regional analog seismic station located in the Baikal Rift system and surroundings at the distances up to 1,400 kilometers. The regional travel time curves for P and S waves were constructed using arrival times registered, and on the basis of this data, regional seismic wave velocities in the Earth's crust and upper mantle were determined, and the obtained velocities are well correlated with the data known on the velocity structures of Baikal rifts. Thank you.
Thank you very much. Next presentation.
Okay, so good morning. We prepared a summary of the historical seismic data for the nuclear explosions that were recorded by the seismic stations on the territory of Slovakia, and totally 448 nuclear explosions were recorded, mostly from the Novaya Zemlya, USSR, and Nevada test site. So we prepared the basic statistics, what is available for the seismic stations on the territory of Slovakia. Thank you.
Thank you. Next.
My name is Sergei Subotin. I work at the Institute of Radiation Safety and Ecology, National Nuclear Center of the Republic of Kazakhstan. General features of areas conducted in horizontal tunnels and vertical boreholes is the fact that radionuclides, cesium, strontium, and plutonium are not carried away from test site borders. At the same time, values of tritium concentrations than more 7 becquerel per kilogram is measured at distance about 20 kilometers radius. The matter is that tritium is a part of water molecules and thus cannot be sought by rock during migration. So it can be moved during migration in significant distance from epicenter. In this case, efficiency of on-site inspection.
Thank you, Mr. Subotin. Next presentation.
My name is Vladislav Sopronov. I'm from Kazakhstan too, as a previous speaker. So I wish to introduce the poster. What will be on the poster session is about dangerous technogenic objects at Semipalatinsk test site. It's very significant to know this dangerous object just because we wish to use lands for activities, and because we must exactly know where we cannot use land and where we can. So please watch to my poster preview. That's all. Thank you.
Thank you. Next presentation.
Good day. My name is Dobe Sergey. I'm from Ukraine, main center of special monitoring, PS45 Malin AKSG. Ukraine experienced two painful atomic explosions. In 1972, in the Krasnograd region, is object Torch, and 1979 in the Yunkom mine near Yuno-Kommunarsk, object Clivage. Nuclear test, they conducted almost in the center of Europe. Thank you very much.
Thank you. Okay, thank you very much to all speakers. And now, coffee break.
Thank you.
Thank you.
That was easy.
Yes, how do you do? Yes. Yeah. Thank you. Thank you. Yeah. Thank you. Thank you very much. Okay. So I have not seen him yet, but I will have. There will be here at this meeting one of my colleagues, Kim Won-Young, and he, like me, will sign up. Practice. You know how he will be the more important person when you have discussions. So he has much more experience than me with actually working with him. But I deeply appreciate that we have this opportunity to get that data, and he will be the person who is the specific person. Okay? Okay? Yeah. Okay. Yes. Yes. Okay. Which station again? Okay. Oh yeah. Okay. Huh.
I think it's
Okay.
distance.
All over the place doing stuff.
Yeah, my family's coming in later this week. Looking forward to it.
Okay, so we start. Hello?
So we're doing things all to the very end.
It's 11:30.
Oh yeah, do we have a little switch? Check, check. 1, 2, 3. Oh, it's alive.
Hello. Okay, it's on. So welcome everybody to this panel discussion on mobile devices as geophysical sensors, promising paths and blinding alleys. I have the pleasure to introduce our three panelists. On the right side we have, Paul Richards. He is an emeritus professor from Columbia University and a special research scientist at the Lemon Doherty Earth Observatory. He has a long history with the CTBTO. He did work as a foster fellow for the US Arms Control and Disarmament Agency in the 80s and in the 90s. He had also made a sabbatical at as a physicist at the Lawrence Livermore National Laboratory. And yeah, we are very happy to have him here. And on my left side we have Stephen Myers. he is the program manager for ground-based natural detonation detection and nuclear test limitation at the Lawrence Livermore National Lab in California. So he's been at the Lawrence Livermore National Lab since 1999, I believe, something like that. So he's focusing on the seismic monitoring with emphasis on technologies to improve the accuracy of event location and characterization of location uncertainties. And on the left side we have, Milton Garces, sorry. He's founder and director of the Infrasound Laboratory at the University of Hawaii in Manoa, and he's also founder and CEO of Redvox, an iOS infrasound app which is available in the App Store and also for Android. And I will give him right away the floor to explain about the app.
Thank you. We're going to do a social experiment now. May I have control of the mouse? We've lost the mouse. Would you be... the mouse is no longer working, which is odd. So, yes, please. Thank you. Murphy. So the aim of this experiment is to find out if we can build a sensor network in this room. What this map is showing is 1, 2, 3, 4, 5 devices that some of them are sitting on this desk. And you notice they're not showing us in this desk because we don't want to display the exact location of these devices. We would like to use that location for doing actual science, but we don't want to chase people around or feel that they're being chased around. So this project was first funded by the US Department of State to develop applications for social applications, for social use. And under ordinary circumstances, I'll show you how to do it. And this one is just as stuck. Okay. So to that effect, we built 2 applications. The first one was in iOS of Apple, and the second one, we released it just this week, is on Android. And what I'm going to ask you is to download them at the beginning of the lecture and just push play and let them play. And we'll see at the end of the talk, or throughout the talk, how many people have actually built this. Under ideal circumstances, I'll be able to actually go up and, look, there's movement on the mouse, and show you what they look like and where they are. And if you have an iPhone with iOS 8 and above, or an Android 7 Nougat, then you can run it. There we go. So please, just type infrasound, either on the Play Store or the Apple Store. Infrasound Recorder, it's got a big red logo, and download and push play. And in principle, you start recording. Now, if somebody will give me a mouse, a little mouse had a cookie. So I'm going to, those of you who are cognoscenti within downloading apps, you will find them immediately, and if I'll leave the floor to somebody else to talk about while we resolve this minor problem. Thank you.
Okay, so Beryl, so next who is going to give us some a short presentation is Paul. So we ask for the slides for Paul.
So the title of the file is PGR Comments.
Yes, I think they are aware of. Yeah, there it is.
So good morning, ladies and gentlemen. I appreciate the opportunity to be on this panel. I remember the first of this series of conferences in 2006, which Ola Dahlman and I organized, and then in later years, an increasing number of people and an increasing complexity. And today, for this panel, you see in front of you 4 very different people. One of us wearing a dress, one of us in a dark jacket, one of us in a light jacket, and a 4th person from Hawaii. So we come from different positions. We come from a background of different experience. And the whole issue, of course, is how can the different talents of the people who contribute to these conferences come to bear on the overall issue of improving the capability to monitor for nuclear test explosions and to build confidence on the system that has that type of responsibility. So to do that, people come from very different backgrounds. I am thoroughly in support of the title that you see in letters on the screen here, but it is perhaps unfortunate that for the next few minutes I will emphasize the last 2 words in this title. I will tell you some rather negative experience that my colleagues and I had in a project 2 years ago when we tested a number of very cheap MEMS devices, and for our purposes, frankly, as I hope to show you, they did not work as well as we would have liked. But as I venture into that blind alley and tell you why I have such a negative opinion of cheap seismometers, I hope you will accept that I am doing this within the larger framework of being quite positive on these matters. So may I have the control for moving forward? Thank you. So over the last few years, recent claims that smartphones equipped with motion sensors offer new opportunities to detect seismic signals. I believe these phones do have some splendid opportunities for the community, but as I will point out, the overall reason we want to do this is to acquire data that we would not get otherwise, and also to involve the general public and not leave just to the expert community this work of treaty monitoring. So I am thoroughly in support of these 2 bullets, these 2 goals. The work that I am describing was mostly done 2 years ago and was prompted by a number of projects that emerged in the years 2013 and 2014. There was an influential article by Sidney Drell and Chris Stubbs on how to detect a nuclear test on your iPhone, a particular publication in 2013, which made this astounding claim that the accelerometer in a 4-year-old iPhone should allow with 95% confidence detecting an underground nuclear test, a small one, not very far away. So let me now use some graphics from the Sandia National Laboratories to describe the underlying microelectrical mechanical systems that are behind a certain type of sensor which does have certain uses, and you see from the graphic the scale here, something very, very small compared to a microbug. There is a moving mass built with usually quartz technology into the underlying integrated device within a cell phone. And there's an equation there which comes from a textbook in which there is an expression for the noise in that type of mechanical sensor, and it is unfortunate for our present technical goals that the symbol M, representing the mass of the device, appears in the denominator, because for a microelectrical mechanical system, M might be at the level of milligrams and is therefore very, very small. And because it appears in the denominator, the self-noise can be significantly large, and there's no way around that. It's a Brownian motion issue. So we can address the evaluation of really cheap MEMS devices by, as the US Geological Survey and others have done, a series of technical analyses like this, but I'm not going to do that. I'm going to describe a project executed in my observatory in New York about 2 years ago. In here you are looking at an optical bench, and at the far end is this drum is a 26-bit digitizing system and a whole system of observatory quality, high-tech, state-of-the-art broadband seismographic sensors. And on the rest of the optical bench, my colleagues, led by Dr. Kim Won-young, place 20 of these cheap MEMS devices, and we operated them for a month just to see. In a typical month, we would expect several hundred interesting signals to be recorded by our state-of-the-art sensor, and how well did the cheap MEMS devices operate. Here's the team. They stuck devices to the optical bench, and the very next day occurred, as a gift from Mother Nature, perhaps the ideal surrogate nuclear explosion signal. What you are looking at here, on the very day after we had installed the 20 MEMS sensors, occurred a deep earthquake at a distance of about 144 degrees, and at that special distance, so the earthquake occurred a distance of 140 degrees from our seismometer, was at this special location where the Earth focuses waves and makes the strong signal you see here. And the earthquake occurred in Indonesia, 144 degrees away from our observatory in New York. And the observatory quality sensors wrote these signals. You see 3 channels for the vertical, north-south, and east-west measurements of the ground velocity, and we also had accelerometers. And here you see on the bottom 6 lines the traces from the observatory quality velocity sensors and the observatory quality accelerometers. And above you see 20 channels from the cheap sensors from a signal, namely the ground motion in New York, that might be expected from an underground nuclear explosion on the order of 10 kilotons at a distance of a few hundred kilometers. And there is absolutely nothing there of any utility in the 20 MEMS sensors. You can do sophisticated analyses to try to see if there's a signal there. We tried that. So I have to apologize for the next graphic. My understanding is that in the diplomatic realm, when one evaluates things, supposing one uses the word maybe something will work, maybe that means no. In the diplomatic realm, if one says yes to something, maybe that means maybe it will work. But in the world of diplomacy, I think it's unwise to say no, this will not work. That's not the diplomatic thing to do. Yet with that background, I offer you my own summary of one of these blind alleys. throughout our deployment, for a month, we had many signals, including the one that I've described to you, from 20 separate channels and gigabytes of data. And the last line is the one that is a very undiplomatic thing to say. My apologies for that. But this is our observation. But the larger picture is that we are trying to do something quite difficult. Seismology is associated with vector motions, and to make a seismometer work, you need to orient it correctly. Devices on cell phones that use pressure sensing, such as Milton Garces has been describing to us, work much more effectively. And so the broader picture, I think, is still that there is an opportunity for citizen networks to contribute. But unfortunately, in the context of cheap sensors for seismology, my conclusion is that this is a blind alley.
Well, thank you, Paul. And now I would like to ask Steve to add his comments on that, and maybe also give a better understanding on citizen science.
Thanks, Sophie. So we've heard Milton describe an app that will allow you to become part of a sensor network, and that is an acoustic signal. And what we've heard from Paul is that if there was a similar kind of app available that allowed you to use your cell phone as a sensor network for seismology, that I think I'm quoting here, it would be useless. There are other applications. I don't disagree with what Paul said. I think the sensitivities, he's done a very good experiment with his colleagues, and if you're looking to detect signals from a great distance that have a lower frequency range than signals that are very close by, that they're just the noise is just simply too high, and even efforts to use many sensors and stack the signals, you're just stacking noise. That being said, there are many analogous efforts in the hazard community to use cell phones and things like that. And when you are very close to the sensor, the source is very close to the sensor, the frequency content is much higher and more suited to being picked up by an accelerometer, which is what's in your phone. That's a completely different study. It doesn't necessarily mean that we will have sensors very close to a nuclear explosion, but the thing that I want to make sure everybody knows is that there is some merit to a citizen seismology network based on cell phones. So there's another option, though, and that option is to not necessarily have people use their cell phones, but it is to develop an inexpensive sensor, yet to be developed, that people could purchase if they wanted to become part of a broader regional or global seismic network and deploy it more carefully than just putting it in your pocket or setting it on your nightstand at night. And you might be able to put it in your backyard. It would have the lower noise characteristics than what Paul described. And then the main challenge would be how to network these things together and how to provide feedback. So as part of a very simple study, I tied up with some colleagues, one of whom was mentioned on Paul's slide, Shri at Stanford, and just did some simulations of what would happen if we had just 1 in 100,000 people participate in a citizen seismology network. And that distribution of people were random over the entire globe. What would the sensor network look like? Of course, it's very dense in urban areas, and it's sparse in rural areas, but there are expectations that there would be unique and new sensor installations in some remote areas. Using those assumptions that distribution of sensors would be random. We just simply looked at the former US nuclear test site and said, what would be the improvement in sensitivity to a nuclear test compared to the IMS? And that being said, there are sensors within approximately 350 kilometers from the IMS from our former nuclear test site. And still, we found through these calculations, using again some Sandia simulation software, that we could potentially expect a reduction in sensitivity of a factor of about 7. Now, is a simulation reality? It might not be reality, but what it does say is that there is the possibility, and that there is, I think, a potential to explore the development of a lower cost sensor, the potential to gauge interest in that. And also, I want to bring up one last point, which many critics have said, well, if you do this, you're just going to end up with thousands and thousands of sensors in urban areas where the noise is high and the interest isn't that high. But there is the prospect of asking people who have the means and who live in densely populated areas to sponsor a sensor in another part of the world where someone is willing to host it and maintain it. And that kind of installation could potentially help the monitoring system quite a bit. That being said, the last thing I'll close with is any kind of cheap sensor is no surrogate for the instrumentation in the international monitoring system. These are state-of-the-art sensors. They're installed in very low noise boreholes, and they are, as Paul showed, sensing signals literally at the noise level of ambient motion deep in the earth. Even a citizen seismology network installed as best you can in the backyard is going to have noise levels that are perhaps 2 to 3 orders of magnitude higher. But, so for global monitoring, a citizen seismology network is probably not going to add much in terms of monitoring the kind of signal that Paul showed. But a citizen seismology network may get enough sensors in close enough proximity to an event of interest to help locate it better, to provide better azimuthal coverage, and potentially to help us understand what the source of a signal of interest was. Most of the time when we see signals, they're false alarms. And citizens who look at signals will probably start to look at squiggles and say, I did this to help with nuclear explosion monitoring, and they'll go to experts and say, I saw something, was it a nuclear test? And almost all the time, it's going to be, no, it was a mine blast near you, it was an earthquake, it was something else. But if we have enough of these and we have a consensus of various sensors around an event, we can say with certainty or very high confidence what it was. And in the event that something does happen, we'll have additional evidence. So there are many blind alleys, and we need to be conscious of that. It's good to do studies like Paul did. It's good to develop these networks like Milton is. We do need to have them rooted in our physical understanding of what generates the sources, signal propagation, what the maximum sensitivity of sensors is. And this is an area that I think is just getting off the ground, so I think it should be pursued further. Thank you.
Okay, thank you, Steve. So maybe the next question would be to Milton, like what makes the mobile device for the acoustic measurement so much better than for the acceleration size sensors?
Just sheer dumb luck, really. It's just, that's part of it. I wanted to show something that it's about 10 minutes old now. Within 2 minutes of you guys contributing, we built that network. You guys did that. So there was no infrasound in this place yesterday. And today, all of you have built a dense network of sensors, and that's about 10 minutes old. Let me see how it looks now. I'm really intrigued. I cannot tell you how happy I was when I first saw that. And now, let's see how many more we have. So that scalability, it's pretty awesome. So, thank you. Thank you for contributing to this. Let's zoom into Vienna. Where are we? Yeah, let me see where we are. And there it is. This is the network we built. Now let's come back. There it is. We are here. So what does it tell you? It tells you the range to each site. It tells you when do you expect the sound wave originates here to be arriving at your sensor. And it tells you the direction of arrival of it. So in principle, you can start locating things. We did this yesterday with SpaceX. SpaceX has been a blessing for us because they advertise it. They have beautiful production values, and they make a lot of noise. So yesterday, I just emailed a few guys, hey, there's going to be a launch tomorrow. And when I was traveling here on the plane, I arrived, and I was like, oh, there's a few phones over there. So we picked it up. And if you are here, the other thing that's really fun is that you can actually look at reports from these things. So if we wanted to, we could generate a report of this, something that happened here. And then look at, for example, this was, come on mouse, come back to me. Yeah, thank you. This one's particularly cool, but this is Friday, June 25, so this is yesterday. And I did that when I woke up at 2 in the morning, you know, because I was a little jet lag coming from Hawaii. And what that shows you, it's all the detections that we had on this network that we built in there. And the closest station is 70 kilometers away. And that is, I mean, it come up overnight and then it went away. Now let's look at an even more interesting one, which is the SpaceX Dragon. What's cool about this? First of all, it's crowdsourced. These are the sensors over there. The furthest one is about 60, 70 kilometers away, so it complements it. And what you can see is the launch signal and the landing of the first stage. How many of you have seen a SpaceX rocket land back on Earth? Tell me it's not the coolest thing. I mean, this was not possible 2 years ago. We could only dream of it. That we can do this now is incredible. That we can collect acoustic signatures from people with cell phones is thoroughly awesome. So we can do this now. You can be active participants. And why we can do this? Because smartphones need good microphones. It's as simple as that. They're voice communication devices, and they're also audio players, and so you need good reproduction. People are doing music recording with low bass. Dubstep has helped us a lot. You want to get the sick bass coming out of it, and you put your nice headphones on, you want to be able to hear that. So the audio reproduction systems have helped around it. The other thing that's helped us a lot is many of you have barometers in your phones, right? So the seed to this concept was after the Chelyabinsk meteor. If you saw the giant sphere over there, right? The case study for that is the Chelyabinsk meteor. So that's about 1 megaton nuclear equivalent. That's 500 kilotons TNT. And that thing went around the world twice. And Kazakhstan was the nearest station. Beautiful record, 600 kilometers away. 600 kilometers away. And I looked at that record and I said, you can pick this up with anything. This thing's just honking loud. It's huge. And Nexus 5 have just issued a barometer native to the Android ecosystem. And I looked at the dynamic range and I said, yeah, we could do this. Thus began that journey. So Chelyabinsk and the IMS network in many ways was the birth of this project in here. And I want to echo Dr. Mayer's position. It's like, we're not going to reproduce, we're not going to replace the systems, but we can supplement them pretty quickly. So if somebody is near a zone of interest and has a smartphone, we can fill in gaps of coverage instantly. You guys did this. I mean, you build a network. How cool is that, right? So you can see that if you log in, and I'm asking people to do so, but if you haven't seen this, okay, so first of all, if you go to the App Store, that's what it looks like. So in principle, you can just push that and download it. And it'll be interesting to see if at the end of this talk we have even more sensors. And if you go to redrock.io, you can get to all of these. Just push one button on your phone, if you're on your phone right now. And the Android app, same thing. If you go to redrock.io, just push that button, and it will tell you whether your system will support it. So a lot of this is happening because over the last 2 years, the systems have changed so much. So as I mentioned earlier, we started in 2013, and this addresses some of the questions. Why is it better? First of all, dumb luck. Second of all, why do they have barometers in pressure sensors, in cell phones, right? Well, for one thing, they want to know on what floor of your mega store you are so they can give you proper targeting on advertising. So they built that for altitude corrections. So it happens that you can also do fitness tracking with it, so count steps. So you keep building better and better resolutions into the barometer. Right now, they exceed the specifications of the meteorological pressure sensors in terms of pressure resolution, and they also exceed the specifications on aircraft flow and pressure sensors. So a lot of my friend pilots are using their smartphones to tell the elevation and also how fast they're going up or down. And if you're a pilot, just download the app and verify by yourself if it performs better. So sheer dumb luck is one. Second one, these things are rotating like every 6 months you have a new smartphone. And they're kind of competing with each other who does the best. When we started this, we were at 16-bit, which was okay. But we're hitting the low frequency noise of the sensors. And then 24-bit was supported. And all of a sudden, we're hitting the noise on the low frequency, and now we got dynamic range. We got another full 8 bits, another byte of information. And so all of a sudden, we keep going down. And so we can go deeper. And it was very frustrating because we started with Android, but then I talked to, we could not record infrasound on Android. And kindly enough, this is one reason why these platforms are exciting. I asked really nicely 2 years ago, could you please change the Android operating system so we can record infrasound? They said, I will look into it. And then last June they said, yeah, we did it. They rolled it out in October on OS 7, so any of you who have Nougat can now record infrasound. This was not possible 3 years ago. This was not possible 1 year ago. And then it takes another month for it to roll out to Samsung and Motorola and all the other things. So about a month ago, it started rolling out to Samsungs. So now you can go anywhere that you have a Samsung and download the app directly from the Play Store. Part of the exciting part about it is that, first of all, the platforms move very quickly. They try to best each other, so if you put a specification in there that has to be met, they will try to do better on it. And the third one is really important, is that it's accessible to all the young people. You are familiar with this. It's a piece of cake to download an app and turn it on. And this is, I think, it's really key for us. Now, there is a lot of art that goes into graphical user interface specifications and design. That's something that everybody in this community can learn from. A lot of our software is pretty kludgy. It's very difficult. Some of the interfaces are a little bit dated. So even if we don't adopt necessarily these more sensors, we can learn a lot from this environment and this ecosystem that rewards ease of use, rewards implementation. So there's a few things in there that we can learn and maybe carry into our community for legacy systems, standardizing infrastructure and standardizing communication protocols, and also power systems. And so these are some of my thoughts. You guys build a network right here, right now. So we can all do this in areas of interest when we really care. And I think that's the primary message I'd like to convey, that now you have it in your hands. And thank you.
Okay, thank you. If there are any questions from the audience, then either you can use the app or you can raise your hand to enter into the discussion. And otherwise, I think that maybe Steve, you have something else to add?
Oh, I was just taking a note as Milton was talking, and I think that the real key is for us to find a commercial need for a better motion sensor in the smartphone, so that the smart guys at the smartphone companies can develop it for us and just include it in phones. But I can't think of what that is offhand.
A lot of the accelerometers are there for gaming, right?
Yeah.
So maybe you can just finesse it, so you don't have to move your thing so much. So part of that is, how graceful. You have a lot of haptic interfaces too that are coming up. So part of that is finding that application, right?
Yeah, we've got to find that application so that they need a higher quality accelerometer or sensor in it.
Like Pokemon Go.
Question over there.
Oh, yes, there is a question for... over there.
Yes, hi, thank you. Thank you for a very interesting set of briefings. Two-part question tied into the comments that were just made. The first part is how much better would the MEMS sensors need to be in a commercial cell phone to actually serve or provide a useful signal at these ranges that you're talking about, these 100 kilometers kind of ranges? Are you talking about maybe a 2 times improvement? Are you talking about a 10 times, 100 times improvement in their sensitivity? And is there a different frequency range? That's the first question. The second question is, has there been consideration of the use similarly to the atmospheric transport modeling community? They leverage a great deal of infrastructure that's out there through personal weather stations and a lot of community-based individuals who go out and invest in putting weather monitoring stations in their backyards. Is there an opportunity there for at least certain parts of the world to augment the accelerometer-based, the seismic-based, by designing something that would become part of perhaps a weather monitoring station that someone might buy and put in their home?
So let me take a crack at that. I would say a factor of on the order of 1,000 improvement is needed, which presents the systemic problem that the self-noise, driven by a formula I had briefly on the screen, which has the square root of the mass in the denominator, means that to make that 1,000 times less of a problem, the mass has to be 1,000,000 times bigger. Or the cell phone is operated at cryogenic temperatures, which is not practical. So it's a pretty strong barrier, in other words. Yeah. However, if it's not rooted in a cell phone, there are a number of commercial prospects of seismometers which have that larger mass to avoid the Brownian motion problems associated with too small a mass. Something too small to build into a cell phone can still be built into something that may not be very expensive. So it's not a complete barrier to make something with a mass on the order of grams instead of milligrams. But then, I completely support the point made by my colleagues that there is merit already in a citizen network devoted to making thousands of measurements of strong motions. So when an earthquake that is felt by 1 million people in Southern California is properly documented by thousands of strong motion sensors, that's a useful activity. But the focus of the technical work for the CTBTO, I think if there's a problem there that we need to address, it is how to always improve our understanding of the recordings of weak motions. And that remains a serious challenge. So I don't see how to make progress there, but I am happy to support all these efforts that go into pressure sensing devices rather than the vector motions.
Let me just second something Paul said, and to give it a little bit more of a feel for people. The citizen seismology efforts for hazard have shown that the accelerometer in your cell phone isn't much better than sensing the motion that you feel from an earthquake. So it does have some utility because it's quantifiable. For instance, something like the USGS, did you feel it? Where somebody says, I felt something, I'm going to report it into the network. That's really useful because everybody says, I felt it, I didn't feel it. When pictures fell off the wall or they didn't, I couldn't stand up, that kind of thing. But the scientific community can do a lot more with the actual motion of the ground. So it is a matter of sensitivity. I have every reason that Paul has the right answer. It would have to be about 1,000 times more sensitive to be useful for the weak motion that's of interest for monitoring. So the idea that, moving on to your second aspect of that question, that's exactly, the weather monitoring network is exactly what we had in mind in terms of developing a cheaper sensor that is larger mass that would be useful for detecting weak motions at greater distance. And really, one of the things involved in that is what is a cost where people will participate. The sensor technology is already there. It's just that most people don't want to spend $10,000 on a sensor that is state-of-the-art and portable. You can get something that's a couple thousand dollars that's also very good, but how many people have a couple $1,000s? So the studies are being started to say, what is that entry point where somebody will say, yes, this is an area of science I want to support. I'm willing to actually spend the money to do it. And the initial guesses are in the several $100s. Guess what you got for Christmas this year? It's a seismic sensor. And then you've got to go install it and have some know-how in how to put it in the ground. And what we were joking before about, don't put it next to the washing machine in the house because all you're going to see is that. You've got to put it in a quiet place. It's got to be thermally insulated and other things. So it's both the price point entry and the ability to install it and keep it maintained, because oftentimes these things get wet because somebody put them in the ground and they gain noise that way too. I think no, do you want to say anything?
I wanted to credit some of my colleagues in the US that I know are pursuing some applications, a very different use case. I think we all concur that sensors on board are just not sufficiently sensitive in the present incarnation. They do have some value for very early warning in some environments. So Richard Allen has been pursuing that in the San Francisco area, and also Ben Brook in South America. I think Chile is his use case. They're looking at magnitude 4s and 5s, and I think Ben is also using the GPS network for looking at ground motion. So these are all things that are being pursued in the US. One of them is from the USGS, and then Richard Allen from UC Berkeley. The concept and the applicability of it is, I think, will remain fertile. It's basically a migration in technology, in form factors, in way you interact with the technology. A lot of the systems that we still have, and we call legacy systems, and the formats that we use are legacies from 30 years, and they're good. They're robust, they're reproducible, they're steady, and there's also new technology coming up, and I think we need to start paying attention to that, specifically how we interact with it, because there's a whole world of coming up that is moving very quickly, and we have to keep up with it. Yeah. Thank you.
Okay, we have another question over there.
Hi, my name is Nelson Zhao. I'm from San Francisco. I'm here with the CTBTO youth group. I have a question regarding detection on mobile phones. Instead of relying on people who would be interested in downloading an app to detect something like this, how about utilizing companies that already require their employees to use a mobile phone, say Uber, who are in more than 80 countries and more than 600 cities with hundreds and thousands of drivers, or perhaps Facebook, who is thinking about expanding all over the world, Google Maps that has cars driving all over the world. How about attaching or utilizing their mobile phones or whatever devices are already in, say, these self-driving cars or the drivers for Uber to detect the infrasound things, and it'd be great for their CSR, great publicity. It's not just for detection of nuclear blasts, earthquakes. So is that feasible? Have you ever considered that? Yeah, thank you.
So it would be wonderful to use the distribution network associated with some of the large companies, as you have outlined. But to be successful in the context of the technical problems faced by the CTBTO to understand even the smallest ground motions, it would be important to achieve effectiveness that these sensors be placed in a quiet environment. So the concept of an organization with thousands of employees driving around the world making deliveries is not the right background. Just to make my point, we are sitting here in this beautiful room with interesting lighting. If I stop talking and we just simply listen in silence for 5 or 10 seconds, this is not a good environment. It's too noisy. I can hear things in the background all the time. So to achieve the effectiveness of the network that you have briefly characterized would require that those drivers with sensors significantly better than can be put in a smartphone be installed nowhere near the garage where their vehicle is kept and so on. So it requires a level of discipline that might not be easy to accomplish.
I'm going to, since I'm on the opposite side of the table and he can't hit me from there, I'm going to provide the counter argument. So it boils down to numbers. So yes, we're going to have a lot of attrition. For SpaceX on Friday, we had 1 of 4 that was usable. The rest was just noisy. That's one more than we had. So if you have 100, if you get 25, okay, I'm pretty happy. If I have 1,000, I get to 50. Awesome. So again, part of that is, and that brings a whole layer of how did you choose what to keep? Which is a beautiful problem to have. Too much data is wonderful. And I mean, Paul comes from a time where things were recorded on paper, and he's doing a lot of recovery of this data. And now you guys are inheriting a world that has an excess of data and a dearth of information. So if you have numbers, you can do almost anything. Then you can say, okay, what is the selection criteria for allowing that? So a classic example was for the Chelyabinsk meteor. Do you know how we wrote that Nature paper? We basically used dash cams and traffic cams. So maybe out of the hundreds to thousands of cameras in Russia, only a few of them gave us usable data, but that was enough to write a Nature paper. You look at the background, you know what that is, you remove it, you estimate the luminosity from it. So we pretty much wrote a Nature paper on YouTube, right? So it is possible. You have to deal with numbers. You have to be able to throw away the junk and be able to recognize the good stuff and only keep the good stuff. So what you're saying is it's all viable, it's all within reach. Bringing it to implementation takes a whole layer of machine learning that we are going to build. Probably you guys are going to have to build it. We maybe get it started. Thank you.
Thank you very much. I'm Mariam from the NDC Comoro Islands. I have a question for Professor Richard. How sensitive what you mean by ship sensors are different from the motion of from volcanic seismic activity or signals to the motion of tectonic seismic activity or signals? Thank you.
So as I understand the question, what is the need to achieve progress with the signals from cheap sensors, not only to detect something, but to detect something with a signal whose quality can be investigated and used to not merely detect, but to discriminate between the types of motion radiated by a small earthquake as compared to the type of motion radiated by a small explosion. So that most of my discussion in the last half hour or so has been on the ability to detect. But to be useful, we want to achieve more than merely detection, but to achieve detection of a signal whose quality is worth analyzing. And so that is a further layer. And again, it is necessary then to go beyond just the minimal detection level, but to achieve a recording that is significantly above background noises and internal instrument noises to enable analysis of the information that is spread out in both time and frequency. So I'm adding layers of difficulty as you hear me describe the challenges of getting something out of a network of cheap sensors. It works just fine, I think, for a community that needs to understand the strong motions from a potentially damaging earthquake, but much harder to do for the types of weak signal that are our current technical challenge in the context of the work of the CTBTO.
Next question. No? There's no microphone? Oh, you were first, sorry.
Yeah, I'm Ilana Tibulak, and I want to ask, what is the corner frequency of MEMS, one of those instruments, and how does that affect the distance from the event where these sensors are recording something useful?
So the word MEMS specifically stands for Micro Electrical Mechanical System. And then within the framework of that acronym, the only way to achieve a useful recording would be to avoid the problems of self-noise. If you require it to be really small, then it's supposed to be really cold. And it's just impractical to operate cell phones at cryogenic temperatures. So I think this is a blind alley.
Hi, my name is Sahil. On a personal note, I'm really happy to see this panel because 2 years ago I was on the Citizen Array panel with your colleague Shri and Dr. Perry. So over the course of from the last SNT to this year's SNT, what has been the most surprising thing that surfaced from your research, whether it's been an achievement or a disappointment? I mean, what has been the most surprising? That's my first question. Second question is, a lot of us that are here from the youth don't have as strong of a scientific and technical background, and we are trying to increase the diversity of disciplines that are here to help science articulate itself socially and politically. So for this topic, obviously 2 years ago when we were creating the panel, we didn't know whether it was just a catchy headline, put sensors in your iPhone and it was something to get people thinking, or if it could actually pan out. So now, given the 2 years of experience more with the Citizen Array, how do you feel like we should be articulating this type of array? Great.
I'll go first, because I think the other panelists want to have something to say too. I want to focus on a couple of things that you said. You said that young people might not have the overall, scientific, physical understanding of what's going on. But when I meet a lot of really talented young people, they're very, very interested in information technology. So the aspect of a citizen seismic network or a citizen acoustic network where the current emphasis on networking can help is with easy communication. I know many people who are interested in knowing about what is happening in the environment around them. They wouldn't mind hosting a sensor, but what they don't want is to just simply put a sensor in their backyard and never hear from it again. They want to see what's going on in their local area, see what's going on in terms of non-proliferation, if that's one of the things that they're interested in. And a lot of these efforts, there was no possibility that they could even be conceived when the CTBTO was thought of. As a matter of fact, if you look at the limited number of stations in the IMS, there are some ways that it was designed that it would not be done that way today because communications were so costly, even for 100 or 200 or 300 sensors. Now we're talking about a network of cell phones or a network that is potentially hundreds of thousands or tens of thousands of sensors. So for somebody like you, I would say help us solve the issue of how to bring all of this information together and also how to most effectively feed back the information that is analyzed to the users in an understandable way. Because that way, I think that you hold people's attention and you really get their interest. There's, you know, the climate is changing, and in areas where there's subsurface injection of fluids, the subsurface is changing too. One of the biggest areas where there is an interest in citizen seismology is in these areas where all of a sudden they're starting to feel earthquakes. So if you can take that same kind of excitement and say, you should be interested in what's going on in the natural environment in your area and show people how they can view what good their sensor that they're hosting is doing, I think that it's something that could really grow.
So I would like to do a little rewind. Some of us remember smoke records. It's a little bit before my time, but I remember seeing them and being impressed with them. And then we entered all very exciting in the 90s, you know. January 9, 2007, the iPhone was launched. Any of you who might remember those times before, flip phones and 8-bit sound and, you know, Trios and Blackberries, really crappy platforms, really, when you think about it, but it's the best we had. It was better than the big blocks that we have in the 80s. So this whole conversation was not really possible 10 years ago. We're looking at, you know, Paul's been doing this for almost 40 years, right? At least, if not, right?
50.
About 20. So this is so very exciting for us, and you guys have the opportunity to initiate dialogues that were not possible when we went to school, when we graduated. So how do you post that? In a sense, you know, if my daughter thinks it's cool, then I must be doing something right, really. But essentially, you get to drive this conversation. You get to decide where we're going to take this and how to make it usable and practical. In the context of nuclear monitoring, you know, we're looking for really sensitive things, very small signals, so it's going to take a serious overhaul of what's possible, or maybe a way to link to them, because there's a lot of wireless protocols that you can use to control very sensitive sensors. And I think that's a really good starting point. And a lot of companies, and I would like to mention RefTech, for example, have a Wi-Fi connection I can control my fancy digitizer with my cell phone. Just that is a GUI stepping stone. It's an experience now that you can start interacting. And I think that's a good intermediate step for a lot of the technology that we have now. Very sensitive, very expensive, but it's a transition thing. And then help us design the next one. But it really is a next generation thing. And we hope you guys are interested in pursuing this with us.
More questions over there? Here.
As we all know that if the radiation level of some cell phone increase a certain limit, so there is a health problem. So if you conduct or if you add or detect the nuclear radiation on cell phone, so whether it is hazardous for the health, increase the level of the hazard for the health or not.
So I think the gist, go ahead.
So I think the question was, might it be possible to have a sophisticated radionuclide detection system in a smartphone? And frankly, I don't know the answer yes or no to that question, but I'll make the point that today's radionuclide detection systems have the ability to work, is it at the level of millibecquerels per cubic meter? Very, very low levels of radioactivity, just on the order of tens or hundreds of atoms. So they have to be really very sensitive, and things have to be very, very clean. So it would be a huge technical challenge.
Yeah, my name's Anton Zhukowski. I'm from the University of Edinburgh, and I have the impression that the panel are talking at cross purposes. So, as I understand it, Paul has said that the self-noise of these MEMS is high because the mass is very small. Now, the self-noise is uncorrelated from one phone to another phone, and so if you are using a lot of phones, it isn't a network, it is just a lot of phones. And the only thing you can do with random noise on all these phones is just simply add up the signals that you see on all of them. And the signal-to-noise ratio goes up as the square root because it's random on every single phone, and they're not organized. So if you have an array of seismometers, for example, and you've got noise, which is propagating noise, then it's organized in some way, and you can do something about it as a network, knowing the position of all the phones. But if you have a network of iPhones, and they each have individual random noise, there's nothing you can do with it except add them up. So when we're talking about we need to increase the power, the signal-to-noise ratio by 3 orders of magnitude, that means you have to have 1 million phones, right? So I would like you to address that question. You know, that it is random noise we're talking about, and having more bits does not change the signal-to-noise ratio. It would help if the noise was organized, but it isn't organized. So, over to you.
So it's a fair question, not that I would say that it shows that the panel is speaking at cross purposes. But to achieve the effectiveness that you have described, those 1 million phones would all have to be oriented in the same direction. And to me, that is impractical, because with the seismology side of things, we're dealing with a vector. It's much less of a problem with using pressure as the signal to be recorded, because that's a scalar, and that does directly add up. But on the seismology side, we're dealing with a vector motion, and that is a real challenge to do the necessary stacking, especially in the context of local structures that don't even make the local vector motion pertinent to some idealized model of a half space.
I agree with everything Paul just said, that essentially the technical challenges of a network of sensors that are in motion at random orientations is, I'd say, challenging. And the thing to add to that is that even the signals themselves across a network of sensors, if you did know the orientation, changes dramatically depending on whether the phone is sitting on a table, sitting on the ground, on the 3rd floor. So even the signals themselves, if you did traditional array processing and just stacked and added them up, it's likely that you wouldn't get the gain in signal that you expect from traditional array processing. So there is signal there. Your point is a good one. There's extreme technical challenges to making use of a network of random sensors as an array. But it's something that maybe should be addressed by some ambitious researcher.
One question over there. Yeah.
Thank you very much for your nice presentation. As you mentioned, there is a very similar network, quake catcher network. This network has many stations in Japan and some stations in South Korea. I want to know whether you have the opportunity to analyze the data recorded by those stations during the North Korea nuclear explosions and the magnitude 7 earthquake in 2016, in order to know whether the results from those stations in Japan and South Korea are as bad as that slide of Dr. Richard. If you can help me, thank you.
Let me go first and say no and pass it to Paul. I've not analyzed them.
So I do not have direct experience with the quake catcher networks you have described in East Asia. I'm well aware that the California Institute of Technology in California in the south and Stanford University in the north, both of those academic institutions organized local communities to record at the level of hundreds, maybe even more, sensors to document what I would call strong ground motions. And within that technical framework of trying to see what is the variability of strong motion for buildings with different foundations, there are splendid technical objectives that can be advanced by the quake catcher networks. But that is a different set of technical challenges from the ones faced by the CTBTO if the goal is to achieve a better understanding of weak signals. To understand weak signals, in my opinion, we need sensors of high quality installed with great care to their quiet condition. More positively, let me say, in answer to an earlier question from one of Svi's colleagues, the high school science environment is potentially an excellent one for informing young people of the potential to see interesting signals in the home and local environment. And it's not necessary to live in earthquake country for a high school teacher to have in the high school a system for recording local ground motions from earthquakes large and small, from the kinds of urban, sometimes catastrophe that happens. The ground moves, and it's very simple classical physics, and for children with imagination and a teacher with imagination, that is an excellent vehicle for spreading the word about the fundamental nature of signals and the world around us. So I think when we talk about sensors at the level of a few hundred or maybe up to maybe $1,000 or $2,000, there is a potential market where those instruments can be sold and a potential audience that can benefit from that type of analysis.
I've seen another rising hand over there.
Zawi Abdel Halim from Military Polytechnic School from Algeria. I have some question. Firstly, do you use some data fusion techniques to don't analyze signal of smartphones separately, but to make a fusion of data to detect the common event and to eliminate all the random and particular signature? And the other question is about, have you investigated the smartphone acoustic sensor for infrasound? And thank you.
Want to go first, Paul?
Okay, I'll answer that one. So the application that's on the App Store and the Play Store uses the internal microphone for infrasound. So yes, and they're available to you now if you want to get them. So they're publicly available. For data fusion, one of the reasons I'm here is because I am representing the Palau National Data Center. They flow in as very different type of structures. Continuous station data have protocols that are, again, they defined 30 years ago. They're very stable. They make assumptions about station locations and their provenance that are not present or possible in smartphone systems. the probability of a vendor giving you their system specifications to a level of detail that you wanted is close to zero. They won't. They have competitive bids for their sensors, and they don't want to advertise what it is. So in a sense, you need a zero-knowledge approach to characterize a smartphone sensor, and so it takes a very different way of approaching things, in contrast to your high-resolution legacy system that essentially the vendor tells you what you need to know to compute a response function. So it's important to recognize the very different types of data that are coming in, and that it requires a very different way of thinking also. Did I answer your question? Thank you.
Any other question from the audience? Okay, then, well, let's say that's it.
I have a question. My name is Karl Koch from Germany. And Milton, you gave a pretty impressive example of a citizen network recording the Chelyabinsk meteorite. And I also had the pleasure over the last couple of years to work with Paul on a seismic event on the North Korean test site that was 100 to 1,000 times smaller than what we knew from nuclear testing. So I have a question. Have you found any example that a citizen network could provide some additional capability where IMS stations are, for example, blinded?
So the talk I'm presenting tomorrow is for volcano monitoring in Southeast Asia. And so it pretty much gives you what is the distance from IMS to a volcanic eruption, let's say 1,000 kilometers. It takes an hour for the signal to get there. That's a little long. Now it's good for basically confirming that a volcanic eruption occurred. Most pilots want more like 5 minutes. You know, so they can redirect their craft and decide to cancel flight or put more fuel on it. And so in that case, time is against us. The speed of sound is too slow. So we actually need to populate areas of volcanic ash hazard a little bit closer to the action. So that's an example where you could supplement the IMS network or other regional networks for a very practical application. Communication can be a challenge in some regions, and that's addressed by using cell phone networks also. So anyway, that's one example, and I'll be talking a little bit more about that tomorrow. Thank you.
Do you want to add anything? Or shall we close? Okay, so if there are no other questions from the audience, then let's close the session early. But I will summarize by saying that for infrasound, the applications, we were very happy that our social experiment here worked very, very well. So thank you for that. And yes, so there are a lot of seismometer apps, but yeah, we have to be realistic, and these are probably not very useful for seismic detection, for nuclear detection, and yeah. So I want to thank all the panelists for their contribution, and thanks for listening.